Hello, welcome back to Mathematical Literacy. I think perhaps I need to discuss more about area and volume and apply some dimensional analysis to it in the context of solving some equations and some problems. Let's look at a circle with a radius of 6.4. Let's say we're working in centimeters. So the radius equals 6.4 centimeters. Now let's take this circle though, and let's turn it into a cylinder. So it will still have the same radius, but we are going to move or to copy that same circle, now flattened. We're going to move it up here and make it part of a cylinder. In other words, we're just extending the base upward to a certain height. We will still have the same radius, top and bottom. Radius will still equal 6.4 centimeters. And let's consider a height of, 17 centimeters. So our volume is going to be the area of the base times the height of the cylinder. Or in other words, when we're talking about the area of a base or the top of the cylinder, we have pi times the radius squared, and then we would multiply it by h. Or in this case, specifically, we'll have pi times 6.4 centimeters squared, the entire thing squared, including the units, and then times 17 centimeters. So that will give us 2,187.553, blah, blah, blah. So I've rounded it to the ones place, and I'm expressing this as I have centimeters squared here and centimeters to the first power there. So I have centimeters cubed. But what if we didn't start with the radius or the height? What if one of those was missing, but we actually knew the volume that we wanted? What if we were trying to design a can with certain dimensions? How high would this can have to be if we wanted the radius to be something specific? Let's try an example of that. Remembering that the formula for the volume of a cylinder is V equals pi r squared h, because we have a circle as the bottom of this cylinder. We're going to try to find the height that a can would need to be if it has a radius of 4.2 centimeters and we want it to have a volume of 665 cubic centimeters. So this would be 665 cubic centimeters equals pi times 4.2 centimeters, all of that squared, times h. All right, now we're solving for h. Pi, remember, is a constant. So we're going to divide both sides by everything except that h. Okay, so pi times 4.2 centimeters squared. That leaves us with just an h on the right-hand side. And then we have some work to do here. 665 centimeters cubed over pi. And what is 4.2 centimeters squared? That is equal to 17.64 centimeters squared. Be careful with your calculator, because we want to make sure we're dividing by this entire denominator. It may help to put an extra set of parentheses there and put it into your calculator as 665. Okay, the centimeters cubed you won't be putting into your calculator, but put parentheses around the bottom and go ahead and do pi times 17.64. Okay, and once again, you won't put the centimeters squared into your calculator. But putting those parentheses in there, make sure you are dividing correctly. And this will give you 11.999, etc., etc. We're going to have to round that. But look at what happens with your units. Centimeters cubed divided by centimeters squared gives you 1 centimeter left. We now have a unit of length, which is exactly what we want for the height. And when we round this, we get our height is equal to 12 centimeters. So height equals 12 centimeters, and that is this height. Done. Let's take another look at that equation for the volume of a cylinder. We have looked at the case where you know the radius and you know the height, and we have solved for the volume. And we just looked at the case where we had the volume, we had the radius, but we were solving for the height. All three of these letters represent variables. Pi is the only constant. V, R, and H are variables in this case. And as long as you know two of these, you can solve for the other one. In fact, for any equation, as long as you know all of the variables except one, you can solve for that variable, no matter how complicated the formula is. So I have a favorite formula for teaching people how to work with formulas, and here it is. It is from Newton's law of universal gravitation, and it states that the gravitational force, represented by F, is equal to the gravitational constant, in fact the universal gravitational constant, times the first mass times the second mass divided by r squared. Now what does all that mean? F equals the force of gravity, G equals the universal gravitational constant, and I'm going to round it a good deal for our uses here. 6.7 times 10 to the negative 11th newtons times meters per kilogram squared. Notice the exponent on that is negative. That means when you move that decimal point, you're going to be moving it to the left. You're going to have a tiny, tiny number. We'll talk about what that means in a minute. So then we have m sub 1. The 1 doesn't mean you raise anything to the first power. It doesn't mean multiply by 1. It just separates the two masses. You have one object, and then you have another object. So you have your first mass and your second mass, or object that has mass, okay? So this could be the Earth and you. I mean, the Earth is much, much bigger than you. So you usually don't realize that that cup you're holding and your body are gravitationally attracted to each other, because the force of gravity between yourself and the Earth is so great that between you and the cup is negligible. And then we have something else that's interesting here. R is a distance. It's the distance between the center of each object. So you are being pulled by the gravitational force between you and the Earth. You're being pulled toward the center of the Earth. The ground is just keeping you from falling to that center. But this formula says you're dividing by the distance squared. That very quickly gets to be a huge number. And that means the gravitational force decreases pretty rapidly as you move away from a large mass. Please notice that in this formula, there is only one constant, just as in our formula for a cylinder, the volume of a cylinder. We had the constant of pi. Here we have the constant of g. A formula does not always have to have a constant, but just recognizing that, we now know that we have force of gravity as a variable. Each of our masses is a variable, and the distance between those two masses is a variable. We have 4 variables in this equation. If we know any 3 of them, we can solve for the 4th. For our first example, let's let m sub 1 be a Math 091 student who weighs 63.5 kilograms, standing on the Earth, and the Earth has a mass of approximately 5.98 times 10 to the 24th kilograms, which is a huge number, okay? And we'll say they're standing at a part of the Earth where they're at sea level, And that means there's 6.38 times 10 to the 6th meters from the center of the Earth, which is also a large number. And what we're looking for is the gravitational force for this situation. Please note that we can rewrite the units of this gravitational constant by going ahead and squaring those meters and kilograms. So we could rewrite this as newtons times meters squared divided by kilograms squared. Why in the world would I want to do that? Because it makes the next thing more obvious. Let's move this over just a little bit. Okay, that was the gravitational constant. That was G. Now we need the mass of the student, multiplying that by 63.5 kilograms. And that mass is multiplied by 5.98 times 10 to the 24th kilogram. Look at that. We have kilograms times kilograms, or kilograms squared. So we're going to get to cancel our kilograms. Okay? But then we have to divide by the distance from the center of the Earth, which is 6.38, what was that? Times 10 to the 6th meters. But remember, in the original formula, that's squared, so we have to square it. And that's going to give us meters squared, which will cancel with that meters squared. I suggest you enter this into your calculator like this. I also suggest you pause the video now so you can enter this. And you should wind up with a force that equals 625 newtons, because all of the other units have canceled. And Newton is a unit of force, which is what you want when you're calculating the gravitational force on an object. So let's look at a different situation with this same formula. Let's say you know the force. So we'll go ahead and put that right over here. The force equals 625 newtons. What you do not know, however, is how far you are from the Earth's surface. Let's say the same student is now higher above sea level, so that instead of the force being 625 newtons, the force, or actually the weight is what this is, of the student is really just 620 newtons at the student's new position. Well, what is that position? How far is the student from the center of the Earth now? We don't know. We can calculate it, though. So let's do that. Okay? But instead of plugging it into this formula and manipulating this formula with all of those big numbers, let's go back to our original formula here and manipulate it to solve for the distance from the center of the Earth. So here's what we're going to do. We have F equals capital G M1 M2. And I'm going to go ahead and put the R in red because that's what we're going to solve for. So in this case, we're solving for that R. It's in the denominator. That's a horrid place for what we're solving for to be. So let's get it out of there. All right, please never divide by a variable. It may disappear and you'll lose one or more answers to your problem. So instead of dividing by this r squared, because we need to take the squared with us for now, I'm going to multiply both sides by r squared. Since I'm multiplying by a fraction over here, I'm going to put it over 1. On the other side, there's not a fraction there. I don't necessarily have to put it over 1. I could do it for both of them. They're a fraction times a fraction, but it's not really necessary. So now, what we have here is r squared, okay, times capital F equals G. Remember that these have canceled. So we just have G times M1 times M2. All right? Okay, so we still have this F that's in the way. We have to get rid of that F by dividing both sides by that. We have r squared equals equals G M1 M sub 1 sub 2 divided by F. But this is a squared R. To get rid of that, we're going to have to take the square root of both sides. So finally, we will get R equals, okay, equals is what we want. Just the R equals square root of capital G, M sub 1, M sub 2. That's all multiplication divided by the force. Okay, on your calculator, that's going to look a little bit different. Okay, we're going to find the distance from the center of the Earth. Okay, to put that into your calculator, though, you will need to use these directions. Please pause the video and give it a try. That will give us R equals 6405883, or let's see, 1, 2, 3, 4, 5, 6. 6.41 times 10 to the 6th meters, which is farther from the center of the Earth than our first distance from the center of the Earth. In fact, this student must be a good ways up the side of Mount Everest. Still 4,000 feet from the top, but getting pretty close. So by moving away from the center of the Earth, climbing a very, very high mountain, this student weighs or has a force of 5 newtons less than the same student would when standing at sea level. So originally we solved for the gravitational force itself, then we solved for the distance from the center of the Earth. You can solve for any of the variables in this equation as long as you have the 3 other variables in the equation. And how did they find the gravitational constant once this formula was proposed? By measuring masses, by measuring the distance between the masses, and by measuring the force between the masses. That's how we came up with the gravitational constant. We now consider it a constant. You don't have to worry about repeatedly doing experiments to find it. Okay, I went through this with really big and really small numbers to show you that it can be done with difficult numbers. Now, thankfully, you're not going to be dealing with things, for the most part, this big in working with these more complicated equations. But now you know it can be done. You can do it. Just remember, as you're working with these, every time you have a new equation, the symbols may mean something different. So just carefully read through the materials. Make sure you know what each variable stands for. Your time working through these, and you'll find out a little bit about what the police and about truck drivers deal with on a daily basis. Please contact me with any questions. I will see you on Monday to begin discussing this stuff.